Hello friends. So this problem is called rotating a rod with a spring and sleeve. So figure shows a horizontal rod mounted on an axis OO dash and a sleeve A of mass M attached to point B by a spring of natural length L0 and force constant K. So we have to find the work required in rotating the rod and attaining an angular speed omega. So what are the things that is given here? So if you see this picture, so basically you have one rod and on this rod there is another rod that is attached. And from this point there is a spring that is attached to this rod. And one end of the spring has a mass M. And this basically sleeve. It can freely move in this direction or in this direction. So this can freely move. So mass is given M and this is A. And natural length of a spring is also given. So L0 is given, that is the natural length of a spring. And mass of sleeve is M, that is given. Now it is said that this rod is rotating with angular velocity omega. Now initially it was rest. Now it has started to rotate and finally this angular velocity is omega. So the questions ask how much work is required to rotate this rod and finally attain an angular velocity of omega. So what we have to do? We have to find work required. So you see, one hint we already have, that is work required. This means we have to use work energy theorem. That is one hint. Now how will you do this problem? So if you see first, this sleeve is moving in a circle. So this will be the circle in which this spring is moving. So this spring is moving in this circle, basically this sleeve. So this sleeve is moving in this circle. What will be the radius of this circle? It cannot be L0. Initial length of this spring was L0, that is the natural length. But now this sleeve has a tendency to move in the outward direction. And due to this spring will stretch. So let us say this spring stretches by an amount x, then what will be the final length? L0 plus x. So what is x in this case? X is elongation. So x is elongation in the spring. So this is elongation in the spring. Now you have to find work done. So how will you solve this problem? One hint, you can use work energy theorem. And since this is moving in a circular motion, so you also have to use circular motion equation. That is force towards the center is equals to mass into acceleration towards the center. That is the force in the radial direction is equals to mass in the radial direction. So let us pause this video and solve this problem. First you have to find x and then you can find the work done. Okay, so let us see, now you have done some work. So you can solve. So first equation will be, since this is in equilibrium, sleeve is in equilibrium, so we can first write circular motion equation. So what will be the circular motion equation? Force towards the center. So force towards the center will be kx, because a spring will apply a force kx. And this is equals to mv square by r, or you can write m omega square r. R is how much? R is L0 plus x. So from here you can calculate x. X will be, so if you take x common, so this will be m omega square. and this will be m omega square L naught. So from here you can say x is equals to m omega square L naught divided by k minus m omega square. So now I know the x. So if I know x, now we have to calculate the work done, work required. So work required will be same as change in kinetic energy. So how much work you have to apply, that is same as gain in the kinetic energy. So this is the work energy theorem. So work required is same as gain in kinetic energy of system. Gain in kinetic energy of system. So how much is the kinetic energy gain? Kinetic energy as well as potential energy, if there is any potential energy. In this case you have a potential energy. So gain in kinetic energy plus gain in potential energy of system, if there is any potential energy. In this case kinetic energy is stored in the sleeve, that is half m b square, and b square is nothing but omega square radius square, and radius is nothing but L naught plus x. So half m omega square L naught plus x square, and potential energy is half kx square. Now we know value of x, so we can simply plug this. So we can have half m omega square, and this is L naught plus x, x is nothing but m omega square L naught, k minus m omega square, and this is whole square plus half k, x is nothing but m omega square L naught, k minus m omega square. So this is the work required. So this much amount of work you have to do, so that finally this sleeve is rotating with an angular velocity omega. Now question for you. What will happen if the sleeve and rod, there is a friction? So there is a friction coefficient that is present. So this friction is present, mu is present between sleeve and rod. Between sleeve and rod. So in that case, how will you solve this problem? Do you have to consider work done by friction also? What will be the work required in that case? How will you write work energy equations? So let us discuss all this in the comment box, and I will see you in the next video. I hope you enjoyed this video, and if you like, please share with your friends. Thank you.